List for the New York Mets, and during which time the team has improved from 71 wins and a last place finish in 2003 to 97 wins last year, and hopefully, although oh no, the Mets, yeah. So in addition to that, he's in his third year as a graduate student in the PhD program in mathematics at City University of New York. And generally when people send their bios to us, they really brag about, as you can see, I helped make a slide to make myself look as good as possible. And Ben sent his statistics. He's been playing in the Long Island Baseball League, the MABL. He plays for the Long Island Brewers, and he posted a 10.29 ERA this year and a .231 batting average. So, so hand it over to Ben.
By the way, if anyone has a score on that Mets game that's going on today, feel free to just shout it out. I'm kind of afraid to check, but... Really? What was the score? 8-0. Nice. All right. No, okay. Okay. So what I want to talk about today is really it's really more mathematical than statistical. So I apologize for that. I don't have a lot of interesting charts and graphs to look at, but hopefully you can bear with me. So I sent this, I wrote up this paper and I sent it to a few people for review, and the overall reception that I received was, yeah, that makes sense, but isn't that kind of obvious? And I guess my answer to that is yes, it is obvious. But I think that in math, at least, if you're looking at a problem from the right way, it's sort of always obvious. It's supposed to be obvious. All right, so without further ado. Okay, so the motivation for this was people have sort of known and figured out long ago that on-base percentage was correlated better with a team's run score than batting average. And people apply that to players to say that a higher on-base percentage gives you a better indication that a player is more valuable offensively, right? And so that's sort of one phenomenon that was observed statistically. That is, people looked at the statistics, recognized that phenomenon. Okay, so I'm not really going to get into that. Just take that as a given for the purposes of this. And the second thing was that something that was alluded to earlier, which was Dips theory, and this let's see if we okay. So this theory was sort of posited by a guy named Boris McCracken a while ago, maybe 10 years ago. And the idea was that he was investigating he wanted to separate pitching statistics from fielding statistics. And what he noticed was that the statistics that described a pitcher's performance when the ball was not put in play were much more, they tended to vary less from year to year than the statistics that involved when the ball was in play. And this sort of flew in the face of, the conventional wisdom about, guys getting ground outs when they need them and things like that. So I was thinking about that, and what you see, so this diagram here is this is sort of a tree diagram explaining all the different outcomes of a plate appearance. And over here we have the events in which the ball is not in play. So a home run is considered not in play because no fielder has a chance to make a play on the ball in general. Those rare exceptions when it bounces off someone's head, we just ignore those. And then over here we have the instances in which the ball is in play. And these frequencies here indicate, this is 71% of the time in the league average the ball is put in play. And 29% of the time it's not put in play. So the overwhelming majority of cases involve the ball being put in play. And so what you see, if you look at the year-to-year correlations between some of these statistics, what you see is that like home runs per plate appearance and strikeouts per plate appearance and walks per plate appearance correlate very well season to season for both batters and pitchers. But what Boris McCracken sort of identified was this ratio of hits on balls in play to balls in play. And what happens when you look at this is that it does not correlate well at all. So what I did was I was looking for a way to express both batting average and on base percentage in terms of these variables, in terms of sort of what you see in this line here. So there's going to be 4 variables. There's going to be walks per plate appearance, and when I say walks, I'm talking about walks and hit by pitches, just because it's easier and the consequences are kind of the same. So it's going to be walks per plate appearance, strikeouts per plate appearance, home runs per plate appearance, and then this hits per balls in play ratio. And what you see okay, so many of you are probably familiar with this already. I just want to run through it briefly. But so this is all batters from 2003 to 2006, and what I did was I took each consecutive season pairs in which a batter had at least 250 plate appearances in each season. So there were 715 such pairs from 03 to 06. And so you can see that the correlation coefficient for strikeouts per plate appearance is very high. It's pretty good for walks per plate appearance. And home runs and hit by pitches, not as good, but still a pretty strong correlation. But when you look at hits per balls in play, the correlation is much, much smaller. And the same thing holds for pitchers, sort of to a lesser extent. The correlations aren't as good in general, but the same sort of phenomenon where hits per balls in play is, you can see the correlation coefficient is pretty small. It's just sort of a blob. And so this is not actually what Boris McCracken discovered or presented in his paper, but it's sort of the same phenomenon, I think, just looking at it sort of from a different way. So I was thinking about that, and what I was able to show mathematically is that on base percentage, the formula itself sort of depends more heavily upon. Oh, I should mention, actually, I forgot. There's a typo in the abstract in the packet. That's 100% my fault. It says. Let's see. It says that on-base percentage depends more heavily upon particularly unpredictable variable, hits per balls in play. That's backwards. It should be batting average. Sorry about that. Okay, so basically all I tried to do was to take the formula for batting average and break it up algebraically into those 4 variables which we identified before. So walks per plate appearance, strikeouts per plate appearance, home runs per plate appearance, and hits per balls in play. And this is all it took. I'll spare you. I'll spare you the algebra, but you multiply by the identity and add the identity and factor some things out, and you end up with this. And I think this line here should sort of make intuitive sense. It's the ratio of hits per balls in play times the ball in play rate plus home runs, right, which are the extra hits that you got. So this is not earth-shattering. But what I did was we can think of this as a function f on it's not literally a vector space, but you can think of it as a vector space on these 4 variables that are between 0 and 1. And what it spits out is a number between 0 and 1. That is your batting average, right? Okay, so you can calculate the partial derivatives, and we'll see sort of some interesting conclusions based on that in a minute. Okay. So then you can do the same thing with on-base percentage. And this is where I think it's not intuitively obvious, I don't think, that you can do this. But as it turns out, you can. So again, it's a very similar calculation, basically. You multiply by the identity, factor a few things out, and you end up with a very similar looking formula, but it's not exactly the same. And so what is the difference? Well, you can reduce it down to this, so that batting average is roughly equal to on-base percentage minus your walk rate divided by 1 minus your walk rate. Okay, so this is the point where you're like, well, yeah, isn't that obvious? And I guess it kind of is, but it's kind of not. So there's a few conclusions that we can draw from this. The first is that if you look at the partial derivatives of this with respect to on-base percentage, you see that the partial derivative of batting average with respect to hits per balls in play is greater than or equal to the partial derivative of on-base percentage with respect to hits per balls in play. And so the sort of interpretation of this is that hits per balls in play is like a bigger component of batting average than it is on base percentage. And because hits per balls in play, as we saw earlier, was such an unpredictable variable, this is sort of why I think batting average is harder to predict than on base percentage. And then, okay, so once you set up this framework and you have everything defined in terms of these 4 variables, there's a few other conclusions, and these are pretty simple derivations that I was able to do. But in this case, you can show that that players who have higher combined rates of walking, striking out, or homering will have a lower partial derivative of on-base percentage with respect to hits per balls in play, meaning that the interpretation of this is that when you are more likely to have plate appearances that result in those at-bats or those outcomes which are more predictable, then your on-base percentage becomes more predictable. And therefore, if you're looking at 2 different players, some players it's easier to predict their on-base percentage than other players based on the types of players that they are in terms of their walk rates and strikeout rates and such things. So it has some implications for evaluating players or predicting them. Okay, and then the other thing that came out, which is sort of counterintuitive, is that under certain conditions, you actually will, if you improve your walk rate, you will actually lower your batting average. And this doesn't, I think, it doesn't really make any sense because walks don't factor into the calculation of batting average at all, right? We're not actually talking about walks, we're talking about the walk rate. And when you define the walk rate, there's an implicit assumption about the relationship between plate appearances and at-bats. And so it just so happens that this condition here is met by 94% of the players in the sample that I had. And so for almost all players, if you improve your walk rate, you'll actually lower your batting average. It's sort of a counterintuitive result. And I have a graph that shows this. Yeah, but, well, I mean, it might not be counterintuitive to you. It seems counterintuitive to me because most people don't think about walks as having anything to do with batting average at all. But, I mean, yeah, again, it does. So maybe it's not counterintuitive to everyone. Right. Yeah. Other things being equal, sure. Yeah. 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 So this is just a graph that shows this. If you don't walk at all, then you start off with the same thing, and as your walk rate increases, you see batting average going down, on base percentage going up linearly. This is sort of where the league average walk rate is. So anyway, that's about all I got. Are there questions?
Did you clarify what your criteria were for people for players that were in your study? Like minimum plate appearances?
Oh yeah, it was 250 plate appearances in each of 2 consecutive seasons. So, you know, I think it was 03 to 06. So it'd be like if 03 and 04 you had 250 at least in both seasons.
Did you happen to look at any correlation between walk rate and strikeout rate?
Not for this because I wasn't really. It's again, it's not really like a statistical thing. It's really just sort of an exercise in algebra. But yeah, so no, not really. Any other questions? Okay. Well, thanks.
Thanks.
Okay, sure.
All right.
Yeah, is it in the back?
Okay. Our next speaker is Professor Jan Boettcher. He received his PhD in mathematical finance from Carnegie Mellon University, had academic jobs at the University of Michigan and Kyoto University before joining the faculty at the Department of Biostatistics at Columbia. So he works in the areas of option pricing and stochastic optimal control. His research interests, of course, in statistics and sports, and he'll talk to us today on probabilistic excitement in sports games.
Thank you for the introduction and an exciting conference in general, in fact. Just one little correction, I'm in the Department of Statistics rather than Biostatistics. Good. Sure. So today, is there a pointer? Oh, that one. Okay, good. All right, so I'm going to talk about a concept which many of you probably sort of feel in terms of if you see a game, how exciting it is or how boring it is. And I'm just going to sort of put quantitative measurement of these concepts. I should mention that this is a joint work with 2 students in our department, Tomoki Ichiban and Mladen Laudanovic. And some of my work in all directions, including sports statistics, is on my webpage. As I mentioned that I'm going to introduce a quantitative measure of the excitement of sports games, and this measure can be thought of as